which is going to be the week of November 23rd. So if we could take it light on assignments for that week, which I think is the last week of the semester, that would be the most helpful, in my
Yeah,
opinion.
I will try not to give anything for the last week of the semester. The only thing that I will try to do, I mean, I will do a lot of reviews and I will ask you to come to the reviews, but I will not try to give you the last week of the semester. So practically what we cover right now is the last material in the class. Now I was hoping that we'll cover more, but that's okay. I think that's gonna be low noise amplifiers will be the last. And I will have one homework more coming this Sunday and one more project on the amplifier, and that's about it. And the only thing that I will ask you to do before the final in the project is just to put things together in a little packet for each one of you. So then I can see from the beginning until the end what each one of you did without necessarily doing more work. But I would like you to put all of the project pieces together in one packet. That's all, with a like half a page summary. And that's what I would like you to do at the end of this class, because then I will review it myself and I will give you a grade for that, putting everything together then. So that's all that I had in mind, but I will, since I know that some of you have all of these things, I will try to make a timeline and then email it to you about what I plan to do until the end of this class and see whether there are any major conflicts. How about that? How we do this?
Yes.
Okay.
Yeah, the biggest
Okay.
thing for us to do is this final demo and the final report, which is...
Yes, I understand. So I'm not going to bug you with anything the last week of our classes anyways. I mean, it's not the right thing for a class to have something major the last week before the final. When is our final, by the way? Do you remember?
December the 1st.
Okay, so immediately after that. So no, not last week, normally I don't give projects or homework.
Second,
I just
sorry.
do review. That's okay. Yeah, it is after the
I'm wrong.
after
Second, not
That's
first.
okay. That's okay. We'll find the exact. I just wanted the week. All right. Anything else about that? So just to repeat, those of you who have a project-related presentation on Monday, you can submit your projects on Tuesday night. All right. I'll make a note so I can email also, though, in case there is somebody who is not connected to this morning, today.
Do you mean the project or homework?
The homework. You don't have a project yet to submit anything. Am I right? Am I right?
Yes, we don't have a project this.
Okay, perfect. Okay, I don't want to get more confused. All right, so no project. You don't have a project to submit. We're talking about the homework for this Monday. Okay. I want to do today, and I will continue now. I will keep hammering you rather, and me myself as well, with examples that have to do with low noise amplifiers. And I like that because, as you will see today, by doing that, we are going to also review everything about matching networks. The only thing we're not going to review when you do low noise amplifiers are filters, but I was hoping that I will cover filters as part of a review. But what we're going to do lots of examples with low noise amplifiers. All right. And so last week, I did an example of a low noise amplifier, but I did not move all the way to the matching networks. I just stopped when we had the circles, both the gain and the noise circles. And now I'm going to do another example, which is at 60 gigahertz. The interesting thing about this is that at the end, I have a paper. For those of you, I don't want you to read the paper, but I want you to see how much now we know. So you really know enough to do a good design of a low noise amplifier. And what I did from this paper is that I extracted some data about the CMOS transistor that they had designed, also the authors designed. And that was a paper they presented in 2007. So obviously it's not necessarily very new for this area. And then from there, we are going to see how we would do the design. Also, as part of this, I have an opportunity to start talking a little more about CPWs. And you will see, I think it will be good for you, since in many, many implementations, especially as you go to high frequencies, you will see more of a CPW than microstrip. And there is a good reason for that. What is the reason? That as you go to higher frequencies, and the wavelength becomes smaller, much smaller, like 60 gigahertz is much higher than 1 or 2, then your substrate thickness becomes, I mean, if you have a substrate that is a 1 millimeter or even 500 microns, for very high frequency becomes a little bit of a problem, because your microstrip is sitting on a substrate that is relatively thick, relatively always, and I will speak about that. So when it is relatively thick, then it loses its good transmission line characteristics because of high frequency effects, which we have not covered. What that means is that the waves under the microstrip change, because in reality, what the microstrip operates because excites an electric and magnetic field, all right, between the signal line on the top and the ground. And when the frequency increases, that electromagnetic field changes its nature. And from being close to an ideal transmission line wave, then it becomes different. And then you have high frequency effects, which means that you have radiation. And then you have increased parasitic capacitances and increased parasitic inductances, and it does not work well. So as you go to much higher frequencies, you will see going to more and more CPW, and as people go above 100 gigahertz, because there is an interesting frequency range, and in 6G practically, that we are going to see in 5-10 years from now, you're going to see more and more circuits above 100 gigahertz, and then you will see CPW. So I wanted to give you a flavor of this, and I used this paper as an example. So in this paper, as it says here, and this is on eCampus, the material, the notes, so you don't necessarily have, just follow what I'm saying, you don't have to copy anything, all right? So what you see here is that the authors who made the CMOS device to have characteristics, so a high FT, so the device can be used for 60 gigahertz, they measured all of the scattering parameters, and the way they present them here, they present the real and the imaginary part, all right? So practically you have magnitude and phase. So then also what they did, as they should, if you try to design for a, get my note, here. If you try to design for a low noise amplifier, what is also of interest is the minimum noise figure, F minimum. Here they call it NF minimum, but it's F minimum. And also, let me see, I move that. And somewhere it goes there. And the also the resistance, the noise resistance for the device. So they give you that as data. Then they did something very interesting, and I put it here because this is what most probably you are going to see if you start working for this in this area. And this is what CPW is, all right? Now, it looks kind of weird here because what they have is they have a lot of measurement circuits, like in the top row here, all right, in this one. they have de-embedding structures. So they call them de-embedding structures, but in reality, it's like I will draw something here to see what it means. I will add a page and I will draw how you measure things in the lab. So if you have a microstrip, all right, this is the microstrip here. You see this microstrip? It's this one here. And I wanna attract your attention to one thing. When you look at, this is not a microstrip, so it's CPW. When you look at CPW, or in the microstrip, or strip line, or slot lines, whatever kind of transmission lines people have used, be careful to see how the authors have indicated the different dimensions. Here I have used W for the width of the center conductor, G for the width of the two grounds. I call them, they are the two side conductors, we call them grounds. And then D, as you can see, for the separation between W and the two grounds. But if you look at other cases, and you will see later, they may have used different letters to indicate those. So be careful to see what they indicate, what letters they're using to indicate the various dimensions. So don't assume that everybody's using the same, especially in CPW. This is true, not so much in microstrip, where H is the substrate thickness, is always the substrate thickness. Epsilon sub r, as here, is always the relative dielectric constant. But beyond that, the rest, in microstrip, W is always the width of the strip, obviously. But in CPW or in other transmission lines that have more than one conductors, in addition to the ground, then be careful and be careful what you are reading. Okay, we'll come back to the air bridge, but let's assume that I have a CPW line, and here I'm drawing that it looks like this, all right? And I want to measure this line. I want to measure the characteristics. So this is the center conductor here, and these are the ground planes, all right? And they are finite in size, obviously. I mean, they will probably stop because you cannot, ideally, they could be infinite, but in reality, nothing is infinite on a wafer. And now I would like to measure it. How do people measure? They come with a probe from a probe station, usually. Probe stations, you may have seen them in the lab. We measure different things. And because this is grounded, and usually there is a ground in the equipment, and on the station, there is a ground somewhere where you put your wafer, they always try to have a hole here on the back side. So if I were to put here a cross section, all right, and this is one ground conductor, this is my center conductor, and this is the other ground conductor. On the probe station where you put your wafer, you sit your wafer, there is going to be another metal, and usually this metal is what is connected to the ground of the system. So what you're trying to do is to open here a hole, at least in the beginning, and connect this ground here in the beginning to the real ground of the equipment. Otherwise, if your ground of your microstrip line does not connect to the ground of your equipment, then it's a floating ground. And for those of you who have done measurements, floating grounds are horrible, because that means that you think it's ground and it's zero potential. But if it's floating, it will have a potential. And the real ground of your equipment is going to have a different potential. So you are going to measure garbage practically, all right? So you do that in the beginning. So these dark things that you see up here, or the square things that you see up here, the pink, the round pink that I have put here. Oops. Okay, this one sometimes is not. So if you look at these round things up here, this is where the round holes that put in the ground. And then you see also that there are 3 squares on one side and 3 other squares on the other. So 4 of those total 6 squares show the ground at the 4 corners, and the intermediate squares, okay. Can you hear me, by the way?
Yes.
Yes.
Okay, because I need to get out of here for a moment because I think it messed up a little bit. Okay. That one is not moving very much. All right, let's see. All right, that may help. All right, so here we go. In the middle square is this one, is here. And usually the probe comes with three, so let me remove now this one so that does not confuse you. The probe comes with 3 kind of 3 fingers. So it's one here, the middle, and the other one. And this is the probe. It looks exactly like that. All right, it's small, obviously. And this one goes to the ground of the system. This one goes to the ground of the system. And this is the floating strip that carries the signal. That's why it's important that this is a true ground, the dark one. And then on the other end, you have another similar probe with 3 fingers. Again, this one goes to the ground, this one goes to the ground, real ground, and this is the center conductor. Ground here, ground here. And then you make that somewhere here, and then you measure the 2 signals in input port, for example, input, output. And then this is called the DUT, device under test. And then you measure, you extract the parasitics from the measurement system, and you find the characteristics of transmission lines of all of the other components. So if you want to make those things, you have to use what they call the de-embedding structure. So you even have to measure your measurement structure, because then you have to remove the impact of your measurement structure from the other measurements. Now, if I grow more, you will see says here, tanks and inductors. Obviously, here is an inductor. If you tell me where's the inductor, is right here. You see that? That's your inductor. And they call them tanks. Why do you think they call the inductors tanks? Because they store energy, all right? It's like a water tank. You put the stored energy in there and you use it. That's why they call them tanks. So usually inductors, tanks are very large inductors. There's nothing more to that. Cascode devices, these are your transistors. Common source devices also. And then capacitors. And these are your single capacitors, you see. Your capacitors are down here. And then you see there are different types of capacitors. One is here that you see down there that I circled. And there is another one there. And so on. And then they measure transmission lines because, as you will see, in a design like this, we use both lumped elements and transmission lines. And we've talked about that. If you remember in the filters, I told you that if you cannot use a transmission line to create a lumped element, then use it as a lumped element. So that's what you're going to see here, that in true designs, you have a mix of lumped elements and transmission lines. So you use what is appropriate. So on this wafer that these authors used, they have to measure everything. The measurement structures, they measure them, and then they measure them so they can de-embed their characteristics from the other measurements. And then so you have clean measurements about the capacitor, clean measurements about your devices, clean measurements about your inductors and everything else. All right? Is that clear of what I wanted to give you an idea of how it really looks if you are to make it yourselves? Any questions about this? We're not going to do this, obviously, but I wanted to show you how it looks. Okay, coplanar waveguides. Also, when you look at coplanar waveguides, sometimes you will see that the line on top of this has those kinds of strips. These ones here. All right, they will look different. They will look like there are strips here and there, and you wonder what they are. And of course, you don't shorten your line. You don't connect all three conductors together to create a short. That's not the idea. What you're doing that is to equalize regularly the potentials of the two grounds. All right, so when do the two grounds may lose their potential? Because the CPW is a symmetric line. So it has two grounds here, one ground here, one ground there. And symmetry is extremely important. Why is that? Because if the line is not symmetric, does not perform as an ideal transmission line. So it's very hard to use it for design. Okay, so whenever I think the two grounds can change their potential, then I have to equalize it again. So when we turn corners, for example, you see that the inner ground has a less path to go around than the outer ground. And if your outer ground runs a longer path, that means that when I come at this point here and at this point there, without an air bridge, as we call those things, you see an air bridge connects the two outer conductors. Without that, the potential between these 2 points will not be the same. And then your line would be okay up to this point, and then after here will not perform. So in corners and places where you do have those kinds of effects, you put the air bridges. Yes. Questions? Okay. Now, let's go back to our problem. I want to get those data that they gave me for the 60 gigahertz CMOS. And I want to use this data. So what I do, I go to the figures and I measure all the scattering parameters in real and imaginary part, because that's what they gave me. And then, excuse me, from those real and imaginary part, I found magnitude and phase. And then I measured also F minimum, 2.1 dBs. I measured it from the graphs. R sub n, which is 18 ohms. You notice it's not 3.5 ohms we had in the previous, it's 18 because we're at higher frequencies. The higher the frequency you're gonna go, the higher your noise resistor. Because all of the higher parasitics you have and the radiation and everything else, everything gets worse in higher frequencies. You need to remember that. That's why designs become so much more complicated. And then in the paper, also they give the value, the gamma optimum, that needs to be given because it comes out of measurements. And for this particular problem is 0.8, for this particular transistor is 0.8, 120 degrees. Also, in this case, which is not of interest to us, they don't have one transistor, they have a cascade device. There are two. And they do that because they provide better noise characteristics and better gain characteristics. But we don't care because the only thing we want to find are the scattering parameters of that configuration. If they give me, it does not matter how many transistors they have, if they give me this data here, then for me, I'm set to do the design of the low noise amplifier. Any questions so far? Okay, now I will do exactly what I did last time, if you remember. First of all, last time I outlined the 6 steps you have to follow. I'm not going to outline them here again, all right, obviously, but I outlined them in this last example we did on Wednesday. And then every time now, since you're learning how to do the low noise amplifier design, you have to follow that example so you don't miss a step. All right, make sure you follow all of the steps. Okay, so here I will cover some of the steps without mentioning them. But after the scattering parameters, the first thing that I do is to draw the noise circles. And also I told you that for you, I will be careful to use the tables. You remember the tables we put together for the noise circles? When we change the value of N, capital N? Yes, do you remember that? Okay. Yes. Do you remember how large or how small the values of N were? Of course, zero, that zero here gives you always the minimum condition, all right, F minimum condition, and RF, which is the radius of this circle, is zero. Therefore, the circle becomes a point. So the center of the circle gives you, for n equals 0, your gamma optimum on the Smith chart. But then after that, you remember I told you that you have to develop this small table before you draw any circles? I did not do it here because I don't have to, but you would need to put a small table so you don't get confused when you try to put the circles, because it's a lot of numbers to manage. Is that clear?
Yes.
Okay. For me, I did not do that here to save time, because I would like also, I mean, assuming that it's the same thing, it's like a recipe. But I have been able here to show you how, using these formulas that you've seen before, I put here all the circles that give me noise. And they're all, you see, all of the centers of those circles are on this purple line. All of the centers of the circles are on this purple line, okay? And the radius of the circles come out of the configurations. And what I have put here is the position of F minimum, which is there. And then the pink and the green circle, F in the pink is 2.7 dBs. F in the green is 3.2 dBs. And as you go out and the circles grow, then you see practically that your F becomes higher and higher. Your noise increases, and the noise figure with that, all right? So up to that point, I did exactly what we did last time. So here. You remember F minimum is 2.1 dBs. For this particular device, you cannot go below that. Okay. Then what did I do last time? I wanted to find what is my maximum values that I could get for my gain circles. All right. And practically, I found GS max, GL max, which are 4.8 dBs, 4.6 dBs, the other one. And if you want to find the highest possible gain for the amplifier, what would you do? Do you remember? Remember the three blocks that I have when I design an amplifier. So if you want to remind you again, I will do it here because we have space and it's in the previous example. So when we design an amplifier, we have the input matching network, the transistor, and the output matching network. Usually we don't need two lines here, we use one, all right? So here, GS max is the maximum I can get out of a matching network like this. GL max is the maximum that I can get from here, considering, of course, the scattering parameters, all right, of this transistor. And how much is G naught? Do you remember? For this transistor?
Magnitude of S21
Exactly.
squared. Yes.
Absolutely. G naught is going to be S21 squared. So practically, after I calculated the GS max and GL max, you sum the two and you add the G naught, and then you find the total, all right, a GT maximum. All right, I did not do this here, obviously, but I wanted to define the gain circle. So obviously I need to define the gain factors, if we remember from the last example. And the gain factors are GS, which is the ratio, it shows us the ratio of whatever GS I can develop over the maximum, its maximum value. So lower GS is always less than 1 or equal to 1 at best. And lower GL is always less or equal to 1, at best is equal to 1. And when it is equal to 1, both RS, or if GS or GL are equal to 1, then either RS is going to become 0 or RL is going to become 0. All right? Now, these are the gain circles. And the gain circles, there are two types, obviously, for the front end and for the back end. But which of the two sets of circles do we really need when we design for noise? Do you remember what I said?
The front one, the input circle?
Exactly. I said that the noise directly impacts the front, the input matching network. So for noise, you do not necessarily need these. I put them here to remind you, but you don't need them. What you need are these ones, all right? And these are the ones, the G sub S is what is important. And these circles that have a center of C sub S and a radius of R sub S are the ones we really need to look at. And what else did we say? That all of these circles have their centers where? On what line? The line that has as a radius, the negative of the phase on the Smith chart, meaning line, the negative of the phase of S11. Do you remember that? Because we see here, see, it's a complex conjugate. C sub S has the phase of S11 complex conjugate. So now if we go here, all of our C sub S circles will be on this brown line here. All right. And also here you have to create a similar table like the one I told you last time. And I just drew, in fact, only the maximum value here, which is the GS. It is not the GS max really. The maximum value we found, let me see how much it was. GS max was 4.8 dBs, all right? So, but I had also another circle which I removed because it was very confusing. But there were two circles. One, in fact, I think I just missed that circle. So I think this circle exists still. And let me do it here. There was a second circle. I did not remove it. It got removed by itself. But the second circle was somewhere where you see that point that I have. Let me just add it here and I'll make sure that you have it in your notes. So I'll put a different color here. Let me use this one. So it's Something like that, it was there. Okay. There was a signal. I'll find it, but for now, let's put this one. And so this circle has 3.59 dBs. And you see, so here what happens with the circles, the noise circles and the gain circles. As the noise circles go away from the optimum noise value, the noise grows, gets worse and worse rather, increases. And as the gain circles go away from the maximum gain value, the gain reduces. There will be, for example, if you see for a noise, which is 2.7 dBs, and that's the pink circle. If I look at the pink circle, which is this one, you see that the noise is F is 2.7 dBs, and it does not intersect with the G sub S circle, which is this one. It does not intersect with this circle at all. So I cannot design for noise, which is 2.7 dBs, and for gain, which is 3.59 dBs for G sub S. I cannot. There is no interact. There is no the two. They don't cut the circles. They don't have a common intersect. They don't intersect rather. So there is not common space on the Smith chart for this. But then I see that if I can take my noise to be 3.2 dBs, and then I can keep my gain to be 3.59 dBs. So I give up noise here to keep a gain. Now, I did that just because I don't suggest that the authors of the paper have done the same. I just did it here. I decided to select this gamma S as a point for design. This is what I decided to do. And after you select your gamma S, and from the two, there were 2 points where the two intersected. Did you see this circle here? Okay. This circle here and the green one intersected 2 points, but I got the point that is closest to the Smith chart. All right, and it's this point here. This point. I got that point that is closest to the Smith chart, as we always discussed. Okay, now what I want to do is take this point and measure and design, I should say, my input matching network. So we remember a little bit about matching networks, all right? And I erased all the other circles because I don't need them anymore. So the point that I selected, if you remember, is this one. This is the point that corresponds to the gamma S that I selected. I still have gamma S, so I need to translate this into an impedance point, all right? Now my impedance, I can read it directly from the Smith chart. How I found also, so every point on the Smith chart has an impedance value and has a gamma S value. Now, in this case, what I did, which is different from what we did before, is I decided to use a series stub. Because why? Because with coplanar waveguide, I have flexibility. I can put both series stubs or series loads as well as shunt. So I decided to go series. I did not change into an admittance. I stayed with an impedance. Okay, so what I know from what we've learned is that if I start at the point here, which is my Z input at AA prime, and this is what I see here, all right? When I start with this, I have from there to go and meet this 50 ohm load. This 50 ohm load, which is the internal impedance of the source, is represented at the center of the chart here. That's where my load is, all right? And then, so from Z input at AA prime, I move along the constant VSWR circle until I find this point here. And then from that point there, I move to the center of the chart. So from Z input AA prime, I move to Z input BB prime, and then I move to the center of the chart. Moving from Z input AA prime to Z input BB prime, as you can see from here, I move from here, there, practically is adding a section of a line. So you see that. And then when I move from Z input BB prime to the center of the chart, the only thing that I do is to add a series impedance. Do you agree with this, what I've done?
Yes.
Okay. And so the next thing is to calculate from the Smith chart the lengths, all right? The length of the line and the length of a stub. But see is what I've done. I thought, well, okay, I have a length of the line which is very small. I am at very high frequencies. So what if instead of using a stub for this one, instead of using a stub for this, I decide whatever that is to represent that element with a lumped inductor or a lumped capacitor, whatever it gets, all right? So I decided to include this section of a line as a line, but I decided to do this one as a lumped element. So in the following, this is what I'm trying to do. And we are going to continue on this on Monday, because I think it's important also, it's a review of things that we've done and how you represent lumped elements. I have a quiz for you, which I want you to have done by Monday at noon. It's very easy. It's a quiz. It's already assigned, has already been assigned. And there are things we discussed today and last time in this quiz. So that is what you have to do. I want to remind you until Monday when we come. And for Monday, as we will continue this, please go and review what you have. All of this is on your eCampus. Look at the previous one on Wednesday and this one so you can follow what I'm doing. Any questions?
Yeah.
When is your office hour?
Yeah, at 3 today.
And
3
also
to
on Monday?
5.
Also 3. Oh, okay.
Yeah, every time my office hours is from 3 to 5, right after every lecture.
Okay, I'll see you on Monday's office hour. Yeah.
Okay, that's fine. Okay. Thank you.
I had a quick question. Do you say
Yes.
the quiz on Monday would be due at noon as opposed to the beginning of class?
Beginning of class. Did I say at noon? I said just by beginning of class.
Okay, I just want to make
Yeah.
sure. Thank you.
Yeah.
I have a quick question.
Yes.
For the current homework due on Sunday, do you want us to design the matching networks as well?
What did I say in the homework?
It doesn't explicitly state that. It just says to design the amplifier. So it's not. I'm not exactly clear if that includes the matching network or just finding.
It would be nice to have the matching network if you can, but practically I'm looking for gamma S.
Okay, but it doesn't give like a substrate or anything. So if we gave matching networks in terms of wavelength, that would be fine.
Yeah, it's gonna yes, because it does not ask you to materialize it, to implement it in anything.
Okay, thank you.
You're welcome.
I have a question about how to determine if we can assume the we can assume the transistor is unilateral?
Where? In the class, where do you have to test? You remember what I said last time? To assume unilateral, you have to check the condition.
Yeah, I know. But there's this little range. There's this range you find using this
U. There is a
unilateral.
U. Yes.
Yeah, U. Yeah, I
Yeah.
calculated that. And
how much is the range you found?
Let me pull up. I think it's it is 0.1853.
So what does it make the error in the gain
Here,
in dBs? You have to plug into one, so it's 1/1 minus U, all of this square. That gives you that is the upper bound, all right? And in the upper bound, if you change that into dBs, you will see how much your error is going to be.
Okay, so if the error is
less than half a dB, you're fine. You'll be fine.
okay,
but if the error is 1 dB, 1.5, then you're not.
Okay, so okay, I'm not quite certain of how this mechanism works.
Tell me how much is your U? Give me the value.
0.185.
How much? Repeat it again. I'm sorry, I could not hear it.
0.185.
185. Okay, so let me see. 1 second here. One moment. I remember what we did here. There.
Yeah.
You see on the right side here. Okay, that part. All right, it's 1 minus, so say it's 1 minus 0.185, and that to the second power. 1 second, second power, and that is inverse, is 1.5, and then we take 10 logarithm. That's gonna be 1.77 dBs. It's a lot.
Yeah,
so you cannot do that, but it's no, I mean, it's not going to change anything. Just go ahead and without making it unilateral.
Okay.
Yeah.
I'm sorry, how did you get 1.77 dBs? I looked away, I kind of missed it.
Okay, so you take the 10 logarithm in this inequality here. In this inequality, you take the 10 logarithm of every part. So the upper bound is going to be, I calculated, 1 minus 0.185. Then I took the second power of this. Then I took the inverse. And then let me do it again. 1 second. It's high, but again, the same. So it's 1 minus 0.185. Okay, take the second power of that, take the inverse. Okay, then take the logarithm, multiply the logarithm by 10, and is 1.77 dBs.
Okay, I think I see where I'm going wrong, because I did 1/1 minus U squared, not 1 over the quantity of 1 minus U squared. So I think that's what I was doing wrong.
Yes.
Okay. Not to hijack Jones's question, but there is, I think, a typo in that U equation up on the top. Is it supposed to be 1 minus the 1 minus S22 squared on, like, with the square on the inside above S22 on the denominator?
Yes. Thank you.
Yeah. Yeah, and I don't know, I think earlier in an earlier notes, it said 1 minus. Yeah. Well, anyways, yeah. No, but I think that's correct.
Yeah.
I found that
There
elsewhere
is
on the internet as
symmetry,
well.
obviously, there. When you see something like that, it's obvious. But in the book, so sometimes, you know, in my notes, I may have some, so you always check the book as well. And
Yeah.
in the book, let me see the book. Where is on the book? Ah, there it is. Of course, it's like it's symmetric, all right? So it has to be inside. And on the
Yeah.
book is the chapter 11, equation 11.46.
Okay. Yeah, I was able to figure that out, I think, just because I
Yeah.
figured that your answer was actually correct and that I went back
Yeah.
and I figured out, okay, that's the issue. So, but yeah, I get that. And I mean, I do have another question, but like I don't want to hold you up. I can ask that in office hours if you want.
Okay, sounds good. Yeah.
So I should ask you in office hours then.
I just have to get off this Zoom and go to another one.
Oh, okay. So you're gonna start your office hours right now then?
I will start office hours. Do you have a problem? I will start office hours. I mean, do you need to speak with me before 3? That's what I meant.
No, not really. No,
okay.
No. So
No
I can totally wait till 3 hours. Just wondering, like, what you prefer.
Yeah.
So
3 will be fine because I need to close this and then also save the recording. Otherwise, it will not save it. And then I would get on at 3.
Okay, sounds good.
Okay, bye.